It's been 5 days. So we're talking about Taylor and Maclaurin series. And what was our goal? Our goal was we want to write a non-polynomial function as a polynomial, right? So we've got some non-polynomial function like an exponential function or a sine or a cosine or something like that. Natural log function. We want to write as a polynomial. And why would we want to do that? Well, polynomials are just more convenient. They're based on basic arithmetic, and they're easy to take derivatives and antiderivatives of, right? So they're just really, polynomials are like the most convenient, easiest types of functions to work with, okay? So that would be one motivation for doing this, okay? And we'll see that in terms of computing, like so your calculator and any computer, when it does calculations, it's doing this. It's reverting to polynomial arithmetic in order to give you answers. Okay, we'll talk about that in a little bit. Okay. So this we said was our general form of a Taylor polynomial. We say this. We want this to estimate some function f. Okay, and then we saw that we have different polynomials of higher and higher degree. Right. So the higher degree polynomial that you build, you get a more accurate estimate of f, okay? And we said it centers at a. What does centering at x equals a mean? It means that it gets the function value perfectly correct at a, and also it gets n derivatives correct at a. And then it gets away from a, then it's not as good as approximation. So your best approximations are around a, and at a it gets things correct. And then close to a, it gives really good approximations, okay, of the function f. All right? So what does it mean to write a Taylor polynomial? It's all about getting those coefficients. And so we worked out last time that the coefficients, that the Cn coefficient, or the coefficient of the term with the nth degree, is the nth derivative taken at a divided by n factorial. We derived that last time. So that's what it means to get so getting the coefficients means that's what you need to write the Taylor polynomial. And then we saw that if you looked at the sequence of Taylor polynomials, higher and higher degree, you get better and better approximations of f. Always the next polynomial will get one more derivative correct, right? So the very first Taylor polynomial is just a constant function at f of a. So all it gets is the function value right. Then the next Taylor polynomial, gets the function value right and also the first derivative, right? So it's the tangent line. The Taylor polynomial of degree 1 is the tangent line. It gets the function value right and it gets the first derivative right. And so on. So every time you do the next Taylor polynomial, you get one more term on your Taylor polynomial, a higher degree of n. You get more and more correct at a, and you get a bigger and bigger neighborhood around a that's good. And then finally, we looked at the limit of that sequence. So if you took the limit of the sequence of Taylor polynomials, you'd have an infinite polynomial, right? Or a polynomial with an infinite number of terms. And that's what we call the Taylor series. And so the Taylor series, it's like this infinite polynomial, and if we can imagine getting all infinitely many terms, then we reproduce the function exactly, okay, within a radius of convergence, okay? And so this is what we came up with for the Taylor series. So that's our nth coefficient, and we're going to sum them all up, starting from n equals 0 to infinity. So this is Cn. Phone calls galore this morning. Guess I don't have my. All right, so this is then the nth term, and there's the nth coefficient. The nth derivative taken at a over n factorial. And we're going to add all those up, starting from n equals 0. And if we could add all infinitely many of those terms together, then that converges on the actual function within the radius of convergence. So what did we do last time? We did e to the, or did we do sine of 1/2 x? Yeah, and we saw that sine of 1/2 x, and we did centered at 1. Was that right? We did sine of 1/2 x centered at 1. And we saw this whole process play out. Okay, so you can watch, I'm not going to get that again, but you can watch the video and see what happened with that. And so if you were to then take the Taylor series of sine to the 1/2 x, the Taylor series, all infinitely many terms added together, would reproduce all of sine 1/2 x perfectly. Okay, but that's a lot of terms, right? That's an infinite number of terms. Okay, so let's do so then we said what was the Maclaurin series then was just the easiest possible Taylor series, and that's with centering at 0. So it gets the function value at 0 correct and the derivatives correct at 0, and then it works its way out from there. Okay, so that was our Maclaurin series. So that's just an easy special case of Taylor series when the center is 0. All right, so we want to write the Maclaurin series for e to the x. Okay, here's a great example because e to the x is kind of, in terms of its values, is kind of elusive, right? So e is an irrational number. So it'd be nice to have it as a polynomial, much easier to work with. So what does that mean? That means we need to find the coefficients, right? So here's our Maclaurin series. So what do we need to do? We need to find these things for e to the x. Meaning we're going to take derivatives of e to the x, and we're going to plug in 0 to those derivatives. And for each one, then we're going to divide by n factorial. Whatever derivative we're on, we're going to divide by n factorial. And once we have those coefficients, we can write down the Maclaurin series for e to the x. Okay? So we're going to start with n equals 0. Then we're going to do n equals 1, and 2, and 3, etc. So I'll go down to 4. And all we need to do is enough to get a pattern, enough so we can see the pattern of what those coefficients are doing, and then write a formula, for this coefficient right here, this expression right here. Okay, so f0x is the 0th derivative or the function itself. So what function are we dealing with here? E to the x. And so then what do? We do e of 0, right? So then f, the 0th derivative, or just the function value taken at 0 is 1, right? E to the 0 is 1. Okay? And then we're going to do so this is now saying when n is 1, we're going to take the first derivative, right? The first derivative of e to the x is e to the x. And so now we're going to take the first derivative at 0. What's the first derivative of 0? 1 again. They're not all this easy. Okay? We'll start with an easy one. Next derivative, e to the x again. Evaluate that derivative at 0. 1 again. I think we have enough to see the pattern. All derivatives of e to the x taken at 0 are going to be 1. That's what we need. Okay? So, what do we got? We've got f of 0 over 0 factorial. So e to the x equals f of 0 over 0 factorial, which is 1. It's 1 over 1 plus, that's going to be 1 again, 1 over 1 x plus, we said all these, so now we're going to have what? 1 over 2 factorial x squared. All the derivatives taken at 0 once, and they'll have 1 over 3 factorial x cubed. And if it's the Taylor, it's a Maclaurin series, that's just going to keep going on and on and on forever. Okay? On and on and on forever. So can we write a general formula now looking at these terms? Can you write a general formula for e to the x? So this is what? This is when zero, we got 0, n equals 1, n equals 2, n equals 3, etc. So now we want to fill in the box here. Now that we're looking at the terms of the Maclaurin series, can we write a general formula for e to the x based on these terms? It's a pretty easy one, right? So this is similar to when we were doing sequences and we're trying to come up with an expression or formula for the nth term of the sequence. Same thing now. So we got the sequence: 1x, 1 over 2 factorial x squared, 1 over 3 factorial x cubed, etc. What's the formula for that sequence then? 1 over n factorial times x to the n. It's a real easy one, right? So I'll just write x to the n over n factorial. So that is the Maclaurin series for e to the x. And it's this polynomial, this infinite polynomial, 1 plus x squared. So yeah, x squared, x cubed, and we've got the coefficients. So it's this polynomial that just has an infinite number of terms. Okay, so now not all Taylor series and Maclaurin series, not all of them converge for all real numbers, meaning they don't approximate the function for all real numbers. There's, like we've seen before in these series, sometimes there's a limited radius of convergence. So we need to find what is the radius of convergence for this, and how do we do that? How do we find the radius of convergence? Ratio test, right? So we're going to do the ratio test. We're going to do the limit as, say, I goes to 0 of x to the I plus 1 over I factorial times, or sorry, I plus 1 factorial times I factorial over x to the I. And that's going to be the limit as I goes to 0 of what? X to the I plus 1 over x to the I gives you an x, right? I plus 1 factorial in the denominator, I factorial in the numerator, I plus 1. And now we evaluate the limit as I gets really big. They don't get easier than that, right? X doesn't care what I does, so X doesn't really come into play here. As I gets really, sorry, what am I doing here? Infinity, right? Ratio test, I goes to infinity. You were all thinking that, right? You were all thinking that. Just forgot that I wasn't perfect. All right. So now what? So now as I gets really, really big, what is the limit? You all should be thinking immediately 0, right? Of course, this is an easy limit. It's 0. And we want to know for what values of x is this thing less than 1, right? So when you get a limit less than 1, we have convergence. So for what values of x do we get a limit less than 1? All, right? This is less than 1 for all x. Doesn't matter what x is. You always get 0 for the limit. Meaning that, what about this Taylor series? Converges for all x, right? So so the radius is infinite. If you were able to add all infinitely many terms together, of this series, you would get exactly e to the x for all x values, for all x values. Okay, so let's let's talk about how computers work, how calculators and computers work. Okay. No, this one. No. Where is it? There it is. Okay. So here is e to the x. How does your calculator graph that? Does it have in its memory banks the function e to the x, and when you type in e to the x, it just retrieves the function e to the x out of its memory banks? No, because there's a whole lot of functions we could put in there. Millions and millions of functions we could type in here. It does not have a memory bank based on names of functions, like thinking of e to the x, oh, that's the name of a certain function, and it goes into its memory banks and it pulls out e to the x, which is labeled, labeled this way. No, it's going to generate this, and it's going to generate this based on approximations, based on series. It uses series to do this. So for example, let's look at e squared. The number e squared, again, does it have this value in its memory banks so that when you type in e squared, it's ready and it spits back the number assigned to e squared? No, it calculates it, right? So when I type in e squared, it's going to calculate it, and it's going to use the series that we just found. Okay, so what series did we just found? We found that e to the x equals. So I'll just write it as a Taylor polynomial. So 1 plus, was it x plus x squared over 2 plus x cubed over 6, and on and on and on. And I'll just make it a Taylor polynomial, so that'll stop at, say, some degree n. Okay? So there's any Taylor polynomial for e to the x. So how does it compute e squared then? How does it compute e squared? It uses this. Okay? It uses this. So then e squared is approximately equal to what? 1 plus 2 plus 2 squared over 2 plus 2 cubed over 6 all the way. Is it going to add an infinite number of these terms together to get us that value e squared? No, that would take forever. That would take forever. So what does it do? It just takes enough to get that many decimal places correct. It's just going to take enough terms. Oh, sorry, 2 to the n over n factorial. N factorial. It's just going to take enough terms until it knows that that's right, that last decimal place is right, and it's going to stop, and it's going to say, here you go, here's e squared. And you thought all along it just was so smart, it just knew what e squared for every decimal place. No, every time you put in a number like this, it does the calculation, just does it super fast. And it's using something, either this or something very similar to this, to generate that number. Okay? So let's see how that does that as polynomials. So I have, here is this what we just found? And I'm gonna choose what capital N is. So as I choose what capital N is, I'm choosing different Taylor polynomials. Okay? So I'm gonna show some more here. So when n equals 0, what am I going to get? When n equals 0, if I just take that's just the first term. In this case, when k equals 0, the first term of that Taylor series. What will I get? What will you see? Yeah, it's going to give me all it's going to get right. It's just going to be what, a horizontal line at y equals 1. I thought. Oh, I got to turn it on. So here's just the first term. All it gets right is the function value at 0, right? Maclaurin series, we're centering at 0. So all that first Taylor polynomial gets is just one term. All it gets right is the function value. Y equals 1. So what about the second polynomial when I do the first two terms from k equals 0 to 1? It's going to get the tangent line. It's going to get the function value, and also, what else does it get right? First derivative. Is the first derivative and the function value right? Again, centered at 0. And you see now that close to 0, it does a good job. If I zoomed in at 0, if I can. Let me zoom in. Here we go. So if I zoom in right there, so now there's a little neighborhood here, like from -0.04 to 0.04, where the polynomial of just two terms, the tangent line, does a pretty good job approximating the function for a little neighborhood there. Okay, and then the second, or when n equals 2, the first three terms, the polynomial with three terms. So what's that? 1 plus x plus. So right now we're looking at 1 plus x, right? This is 1 plus x. And then the next Taylor polynomial would be 1 plus x plus what? X squared over 2. That's a quadratic approximation of e to the x centered at 0. You see it has a bigger neighborhood where it's doing well, right? A bigger neighborhood where it's doing well. And now it has the function value and the first two derivatives exactly correct at 0. Next Taylor polynomial will be the same thing. Now I'm going to add, it's like a sequence, right? It's a sequence of polynomials. This is a cubic. Now it's doing a good job. It's got the function value and the first three derivatives correct at 0, and then it's doing a pretty good job all the way from -1 to 1 of reproducing the function. Okay, and then, so as I continue to take larger Taylor polynomials in more and more terms, I mean, even if I get to 10, it pretty much converges. We're doing a great job from all the way from -3, and who knows here, but it's like landing right on it now. I can zoom out. We can see that here at -4.5, it's tailing off. But again, with longer and longer, more and more terms, it's going to do a better and better job away from 0. And if we could have the sum of all the terms, it would give us e to the x exactly, right? It would give us e to the x exactly if we could take all infinitely many terms. So that's how it's approximating the function. But what about e squared? So let's go back and look at, we were talking about e squared, right? So I'm going to plot a point on the approximation. So, and let's plot actually e squared too. So this point on the red graph is displaying a representation of the exact value of e squared, the y coordinate of that. And for our first term gives us e squared as 1. So this f of 2 is showing the current Taylor polynomial, what it's giving us as an approximation for e squared. Not very good. Okay, so now if we do 1 plus x, still not very good. It's giving us a value of 3. Okay? But every time, so now it's giving me a value of 5. When I have the quadratic approximation, first three terms, 1 plus x squared over 2. Here's n equals 3, doing a lot better now. So now we know e squared is about 7.389. The cubic Taylor polynomial gives us a value of e squared of 6.33. 7 versus 7.389. N equals 5. And so we see that it's converging, right? It's converging very quickly here. So let's just jump to n equals 10. Here's n equals 10. And it's correct to how many decimal places? About 3, right? So now when we take the 10th Taylor polynomial, it's getting e squared correct to about 3 decimal places. So how many terms do you think we're going to need to get this many decimal places correct, right? To get it all the way to this decimal place right here? Try 15. N equals 15. Does n equals 15 get it? Almost, right? It's just that last decimal place. So how about 16? 16 gets it. So for calculating e squared, it's gonna take this Taylor series, and it's going to take Taylor polynomials, and it's going to take 16 terms, and it's going to know by error calculations. Remember Dr. Thompson was talking about error calculations. It does error calculations to see that the error is less than this decimal place worth of error, and then it stops. It's only going to take like 17, n equals 16 means 17 terms. A polynomial with 17 terms, or to the 17th degree. Polynomial of 17th degree, 16th degree, 17 terms, 16th degree, and it knows that it's got its approximation of e squared to that many decimal places, and it just stops. And it says, here you go, here's your e squared. Okay, so super important, right? So this is really, really relevant because this is how computers calculate. And your calculator, it's how it calculates. They use series. And they just get good enough approximations to give you all the decimal places correct, and then they stop. Yes, sir?
If this weren't a Maclaurin series, how would we know where to put A and have that axis of rotation exist?
Maclaurin series is always centered at 0.
No, if it weren't, if it was just a regular Taylor series,
yeah.
How do we know where A is supposed to be at?
You choose. So what do you want to do? So like you could do the Taylor series, and you could do centered at 1, centered at 10, centered at -5. So it's just before you start, what's that?
Why would we choose a particular number? Why would we choose A at 5 or A at 7 or A at -3?
Okay, so if you wanted to estimate e to the 50th, you wouldn't use a Maclaurin series because it would take too many terms to do it, right? Or no, so like say say you want to do e to the 50.02. Then what center would you choose? If you wanted to estimate e to the 50.02. You would choose 50. And then even the linear approximation, the Taylor 1 plus even the linear approximation, the 2 terms, right? 1 plus would be a very good approximation of that, right? Because it's so close to 50. So if you had a particular approximation that you wanted to do, you would choose your A as close to that as possible. And whole numbers are convenient. So that's why I'm saying choose 50 to be. Choose a whole number that's convenient, and that would be Taylor polynomials centered at A equals 50 would be a very good approximation for e to the 50.02. Does that help?
That makes sense.
Yes, sir.
So a computer calculates e squared by comparing what it gets to the actual value?
No, it doesn't know what the actual value is. It does this process right here. So I'm showing you. So this thing right here, I set n equal to 16 right now. N is 16. So when you take the first 16 terms of this thing that we found was e to the x, here's what it gets. So that's what the computer is doing. When you put in e squared, it's doing this. It's calculating this. It doesn't know what the exact value is. It's calculating it with a series.
So if you want the closest approximation, you would want x to be closest, or a to be closest to x, the x that you want.
Right. Because you're watching it happen, right? You're watching whatever you choose as the center. The center is what it gets everything perfectly correct, and then look at a neighborhood around the center. It's approximating the function values correctly for a neighborhood around the center. See where it's kind of like indigo? So you wouldn't use the Maclaurin series, say, to estimate e to the -8th. You'd do a Taylor series and center it at -8. And then it would do the same thing as it's doing here around 0 at -8, and then you'd have really good function values estimates around -8. Another question. I saw another hand. Anybody else? Okay, so why don't you guys try Maclaurin series for cosine x. Maclaurin series for cosine x. while I take attendance. Here we go. We got one more example to do. Okay, I'm going to go fast because you worked on it. All right. So n equals 0, 1, 2, etc. You just need as many as you can establish a pattern. Okay, so 0th derivative is cosine. Taken at 0 is 1. First derivative is negative sine. Taken at 0 is 0. Second derivative, negative cosine, negative 1. Third derivative, positive sine, 0. Cosine, 1. Okay, do we see the pattern yet? Okay, so it goes 1, 0, negative 1, 0, 1, 0, negative 1, 0 for our nth derivative at 0. Okay, so now you write the Taylor series. So we say cosine x is approximately equal to, okay, 0th derivative is over 1. It's going to be 1 x to the 0. So we're going to start with 1, right? And then we're going to have plus 0 over 1 factorial x to the first. I'll just write it out just so we see what we're doing. And that's just going to be 0, right? And then what we have is minus 1 over 2 factorial x squared. And then we're going to have another 0 over 3 factorial x cubed. And then what's the next one going to be? And we have the 4th power. Plus 1 over 4 factorial x to the 4th. And then we'll have another 0 term. What will the next term be that's non-zero? Minus 1 over 6 factorial x to the 6th. Okay, so before we kind of resolve this into a formula, this one's a little bit trickier, but before we do that, talk about web work. In your web work problems, they're often going to ask for, these coefficients, C0, C1, C2, C3, etc. What they mean is, so Cn is always the coefficient when the power of x is n. So if they say Cn equals, they're asking for Cn, they're asking for what coefficient do you multiply by to get the nth power term. Okay? So for instance, what do we multiply? What's C3? So what are we multiplying by x cubed? That's what they want for C3. So what do we multiply by x cubed? 0. So you're going to put in 0 for this one in web work. What do you multiply by to get your x squared term? Being negative 1/2. What about to get to the first power term? 0. The 0th power, 1. So, and then C4 would be, one more, let's just one more, what's C4? 1 over 4 factorial. Remember, in web work, you can put expressions in. You don't have to have a handheld calculator sitting next to you where you're punching in, getting a decimal approximation, and then putting it back in web work. You can put in expressions as long as you want and use the answer preview button. Let web work be your calculator for you. Because then you don't have to worry about decimal places. You don't have to worry about a punching error. You can use the preview and make sure it looks exactly like you're intending. Okay? Use the preview and let web work be your calculator for you. So expressions like 1 over 4 factorial is perfectly fine in web work. If that gives the right value, then you get it correct. Okay? Okay, so now the question is, so we end up getting 1 minus 1/2 x squared plus 1, so let's write it as factorial, 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th, so, etc. So if we were to rewrite this now, So in web work, this is what you need for your answer. So you would just need your coefficients, and you're going to include the zeros where you get terms that zero out. But if I wanted to write this now as a series, so that what? So that this is the 0th, and now this is the first, and this is the second. We don't want it to skip and give us zeros every other time. We just care about the non-zero terms. So I'm going to write a new series, so I'm going to write a sequence that has this formula. The 0th term is 1, the first term is that, the second term is that, the third term, etc. Okay, so I'm going to write a new series now based on the sequence where 0 gives 1, 1 gives this, 2 gives this, 3 gives this, etc. So can we do it? So I'll do, say, I equals 0 to infinity. And now looking down the road here, first of all, it alternates. So we're going to have negative 1 to the, will it be I or I plus 1? So the 0th is positive, the first is negative, the second is positive, the third is negative. So that will just be negative 1 to the I, right? That'll get the alternating that we want. Okay? And so now, what will the formula be? So the first, so when I equals 1, I want 1 over 2 factorial x squared. When I is 2, I want 1 over 4 factorial x to the 4th. This is easy, right? When I is 3, I want 1 over 6 factorial x to the 6th. So I want, what, x to the? 1 gives 2, 2 gives 4, 3 gives 6, 2i. The denominator will be 2i factorial. 2i factorial. It's supposed to be an I. So you see what I did? So now this gives the exact same terms as the Maclaurin series does, but it doesn't give me all those extra zero terms, every other one I don't want. So this will just give me the non-zero terms of cosine x. And so this is the Maclaurin series for cosine x. Okay, to get the radius of convergence, ratio test. This one, again, this one will also converge for all real numbers if you do the ratio test. Okay, any questions on that? What I did. So in web work, it'll often ask in this form. You wouldn't have to do this. But this is a much better way to write cosine x because it doesn't give us 0 every other term. I got one more thing to do. Don't back up yet. Any questions on this example? Okay, so now we've derived the Maclaurin series for e to the x and for cosine x. And so these are really basic ones. And so what happens is, going back here, so we have these formulas for the basic, real basic functions. E to the x is this. Cosine x we just derived. Sine x is easy to also derive. And so what we can do is, now we can use the formulas that we derive to find series for other things that are similar. For instance, if this is e to the x, then what is e to the negative 3x? As a series. We don't have to start from scratch. If we know what e to the x is, we can just write down e to the negative 3x because this is, right, our exponent is x here is our, what, argument. Now our new argument is negative 3x. And so it's just like we've always dealt with functions in the past. What will it be? If it's e to the x is x to the n, then e to the negative 3x is negative 3x to the n over n factorial. We just wrote the Taylor series, the Maclaurin series, for e to the minus 3x, based on e to the minus x. Okay, what about x squared times e to the x? Can we write a series for that? So if e to the x is a polynomial, if it's a sum of terms, what does it mean to multiply x squared times a sum? What do you do? So if I have the sum, and I multiply it by x squared, then what happens? Yeah, distributive property, right? The x squared will just get multiplied by every term. So then we can just take our x to the n. X to the n becomes what? Two n? This is n number of x's multiplied together, and what are we doing? 2 more multiplied. So it'll be n plus 2 over n factorial. So I didn't have to start from scratch, and that would have been ugly too, because all these derivatives would have been this expanding product rule, right? Product rule on product rule on product rule. You don't want to make that table for this, because those derivatives would be really ugly. So instead, we can just use the Maclaurin series for e to the x, and this just says multiply every term by x squared. So there it is. There's the Maclaurin series for x squared e to the x. What about e to the x minus 1 minus x? Notice e to the x is this. What would it be? What would it mean if it was e to the x minus 1 minus x? Exactly. So e to the x, so I'll do it in red. E to the x minus 1 minus x would just be this thing, e to the x minus 1 minus x. So it would be this. That would be your Maclaurin series for that function. Just e to the x, take away the 1, take away the x. The box that I put in red, that would be your Maclaurin series for that function, e to the x minus 1 minus x.
Would you just write the sum as n is equal to 2?
You're right. You could do the sum and then start n equals 2. Exactly. Okay. Web work on this stuff for Wednesday. Wednesday web work.